In this video, we'll take a look at the Heathkit ET-3400 Microprocessor Trainer, also referred to as a Microcomputer Learning System. While they had offered some instructional materials as early as the 1950s, in the 1970s, Heathkit got more seriously into the educational market, offering a series of courses on electronics. Part of the offering was a series of hardware experimenters or trainers, which provided a platform for performing the labs in the courses. They typically included power supplies, input signals, and a solderless breadboard. Different trainers were targeted at analog and digital electronics. With the advent of the microprocessor, they expanded the line of products and training courses to include hardware and software specific to microprocessors and microcomputers. In 1977, Heath introduced the ET-3400 Microprocessor Trainer at a price of around $200 US. It was built around the popular Motorola 6800 microprocessor and included an LED display and keyboard for entering and running programs. A breadboard area allowed the user to perform hardware experiments and gain access to the signals of the microprocessor. An extensive training course, the EE3401, was offered that taught microprocessor hardware and software using the board. It came as a set of binders, cassette tapes, and all the electronic components needed for the labs. The course cost about $150. Like most of their products, the ET-3400 was sold as a kit that the user would assemble. A factory-assembled version, the ETW3400, was also available at a higher cost. The trainer was expandable by purchasing the ETA3400 memory and input-output accessory, which added additional ROM and RAM, a serial port for communication with a serial terminal, and an interface to allow loading and saving programs to cassette tape. This made the unit more convenient for programming and also offered the tiny basic programming language in ROM. The ETA3400 expansion cost about $175 and another $50 for the additional 3K of RAM memory. The ET3400 was slightly updated as the ET3400A model around 1981 or 82. The ET3400A used the 6808 version of the 6800, which included the clock oscillator, which had required an additional MC6874 chip on the ET3400. It also ran at a 1 MHz clock rather than the 0.5 MHz of the ET3400. The ET3400 could be modified to run at 1 MHz using a crystal. The ROM was changed from a 1K MCM6830A to a 2K 2316, which was compatible with commonly available 2716 EEPROMs. It also switched from 2112 256 by 4-bit static RAM to 2114 1K by 4-bit RAM chips, offering 1K of RAM as standard. Around 1982, Heathkit also introduced the model ET6800 Trainer, which was essentially a cost-reduced version of the ET3400, which had the same 6800 CPU but only provided a hex keyboard and LEDs, and not any of the hardware prototyping features. It sold for about $100. The basic features of the ET3400 are the following: a 6800 microprocessor running at 0.5 MHz, a monitor program contained in a 1K ROM, 256 bytes of RAM expandable to 512 bytes, yes, bytes, not megabytes or kilobytes, 6 7-segment LEDs for display, a 16-key keyboard plus reset key, a breadboard area for prototyping circuits, 8 LEDs that can indicate logic high and low levels, 8 dip switches that can produce logic high and low levels, access to all address, data, and control signals on the breadboard, access to ground, plus 5 volt, plus 12, and minus 12 volt power supplies. The plus and minus 12 volt supplies are not required by the unit itself, but can be used by some of the hardware experiments. 1 Hz and line 60 Hz clock signals, an optional expansion connector for use with the ETA3400 memory I/O expander, a power-on standby switch with power LED, and a self-contained power supply. Everything's contained in a rugged and compact plastic case, and the unit weighs about 4 pounds. All ICs and the LED displays are installed in sockets, and the chip functions and signal names are listed on the board silkscreen. Let's take a look inside. The same blue case was shared by some other trainers like the ET-3400A and used a blue plastic common with many Heathkits of that era. Most circuitry is on one double-sided printed circuit board. Some power supply circuitry is on a metal bracket which also acts as a heat sink for the regulator. Two smaller regulators are mounted on the edge of the board adjacent to ventilation holes. The dangerous AC voltages for the power transformer and power switch are inside an enclosed unit. The keyboard keys are on a small printed circuit board so they could sit flush with the top of the main board. A few ICs at the top are hidden behind the case and not accessible from the front of the PCB. At the bottom is an expansion connector for the ET-3400. This board has some jumper wires and one IC added, which I'll cover later. Let's take a look at the unit in operation. The power switch is actually power on and standby mode. In the on position, all circuitry is powered up. In the standby position, the power is off to the LED displays, but the CPU and memory are still powered up so that any program that's been entered is still retained. The unit must be unplugged to fully powered off. On power up, the displays will light up in a random state. You need to press the reset key in order to reset the CPU. Doing so should cause CPU up to be displayed on the LEDs. Note that we can turn the power switch to standby and see the LEDs go off. If we turn the power switch back on, it returns to the same state since the CPU continues to run. A handy feature is the two segment test pins adjacent to the display. Shorting them together will cause all display segments to light for test purposes. They'll stay lit until you hit reset. Before demonstrating the CPU, let me show some features of the breadboard. The large solderless breadboard is for installing components for lab experiments, either those in the EE-3401 course or your own. Above the breadboard are solderless holes for the address lines A0 through A15, and to the left of that, the control signals like reset, read-write, halt, and interrupts. At the upper left is access to the data lines, and below that, clocks for the CPU phase 2, a 60 Hz line clock, and an approximate 1 Hz clock. At the lower left is power consisting of ground, plus 5 volts, and plus or minus 12 volts. An 8-position dip switch allows generating low and high logic levels, and 8 discrete LEDs indicate the level of the switch and can be toggled. For example, we can connect a jumper wire from one switch to an LED. The LED will indicate the level of the switch and can be toggled. If we connect the LED to the 1 Hz signal, we can see it toggle about once per second. Finally, if we connect an LED to the reset signal, we can see it go low or off when the reset button is pressed. Now let's look at how the unit's programmed. I'll assume you know something about the 6800 processor or microprocessor machine language programming in general. If not, you should still be able to follow most of this discussion. The hex keypad is used to enter data as well as selecting functions. Each key has a hex value as well as an abbreviation for a function it can perform. The 6 7-segment LEDs are used during programming, typically showing addresses and data. They can also display alphanumeric characters. Pressing reset will put the unit in a known state. From here we can press a number of keys. Accumulator A or 1 will display the current value of accumulator A, in this case the hexadecimal value of 31. Accumulator B will display the value of accumulator B. PC will show the program counter, which is 16 bits, and currently has the value 0000. Index will show the X or index register, which is also 16 bits in size. CC shows the condition codes, An 8-bit register of which 6 bits are used. The value displayed consists of ones and zeros, and the markings next to the LEDs indicate the register bits, H, I, N, Z, V, and C. Pressing SP will display the stack pointer. To examine memory, we can press E or examine, and then enter a 16-bit address. Let's use 0000. We can see that the current contents is FF. We could change the contents of memory at that address by pressing C or change and entering the new 8-bit hex value, let's say 55. Pressing forward will display the contents of the next location, 0001. We can do that as many times as desired. Pressing back will display the previous memory location. If we go back to address 0, we can see that it indeed contains the value of 55 that we entered. Using these keys, you can see that it's possible to enter programs into memory, provided that you've determined and written down the machine code as hex bytes. The manual for the ET-3400 includes a number of programs. You can, of course, write your own. Typically, you need to enter several dozen hex bytes. To streamline this process, the auto key can be used. It will prompt for a start address and then allow you to enter consecutive hex bytes, automatically incrementing the address. Here's an example of entering some bytes starting at address 0. So we can now enter the bytes, let's say 01, 02, 03, 04, 05. When you're done, or if you make a mistake, hit reset to get out of auto mode. You can then use the examine key to review if you correctly entered your program and make corrections if needed. When you're ready to run your program, hit the Do key and enter a 16-bit address. After the address is entered, it will start execution. The ET-3400 supports a few more advanced features to make programming and debugging easier. The break key allows you to enter the address of a breakpoint. When your program reaches the address of the breakpoint, execution will stop and return to the monitor. You can then examine the contents of the registers and memory as desired. You can have up to 4 active breakpoints. Pressing SS or single step at this point will single step your program one instruction, a very useful debugging technique. Note that breakpoints must be in RAM because they're implemented by writing a software interrupt instruction at the address. The single step function, however, does support single stepping through code in ROM. Finally, pressing RTI or return from interrupt will cause your program to resume execution after hitting a breakpoint or single stepping. With these functions, you can enter short programs, debug and verify them, and learn 6800 microprocessor programming. The memory is limited to 512 bytes, but this is adequate for running small programs for educational use. Let's look at an example. The first example program in the ET-3400 manual is one that turns each LED segment on and off in sequence. It's 36 bytes in length. I'll enter the program using the hex codes in the manual using auto mode. After entering the data, it's a good idea to check the program before running it. Finally, let's execute it. We hit Do and the start address 0000. And as we see, each of the LED segments is lit up in unison, and the software then repeats continuously. I've now entered another example from the manual. This is a number guessing game where the computer generates a random hex number. I press a key to make my guess, and it will indicate if my guess was correct or if it was too high or too low. we start at address 60. We press a key and it will generate the random number. And now I make a guess from 0 to F. Let's say 8. So that's too high. How about 5? Still too high. 2. Still too high. 1. And yes, that was it. Press the key again to start. Let's guess 7. Too low. How about C? Too high. A. Too high. 9. Yes. The manual includes 7 sample programs, and the EE-3401 course, which you can find on the internet, has many more programs, as well as hardware interfacing labs, some of which are quite advanced. I've been looking for an ET-3400 or ET-3400A for some time on eBay, waiting for one that would come up at a reasonable price, including shipping to Canada. In July 2018, an ET-3400 showed up from an eBay seller in Toronto, and I purchased it. It looked complete except for missing the manual and the ROM. The seller said it powered up, but one LED was not working. It arrived in good condition, and I took a look at it. It showed signs of normal use, but was in quite good shape considering it was somewhere around 40 years old. After inspecting it, I powered it up carefully with a Variac. The power rails looked good. As the seller reported, one LED didn't light even when using the segment test pins. Obviously, it would not come up as the ROM was missing. Some immediate good news was that the LED problem was caused by a bent pin. Removing the LED, straightening the pins, and reinserting it got all segments to light. The LEDs and dip switches were working, and the clock signals looked good. I gave it a minimal cleaning inside and out. The biggest challenge, which I had anticipated, was the missing ROM. It was originally a masked ROM, which was manufactured for Heathkit and unique to this kit. On the later ET-3400A model, the ROM used was compatible with 2716 EEPROMs, which are still available and can be programmed by the user. However, the ET-3400 used a MCM6830A ROM, which has an entirely different pinout from a 2716. Studying datasheets and doing some research on the internet, I came up with a way to rewire a 2716 in place of the original ROM. Once the 2716 arrived, I erased it with my UV eraser and then programmed it using my PROM programmer. Note that the 2716 is a 2K EEPROM and the original was 1K, so I only needed to program the upper half of the ROM. Fortunately, the code for the original ROM was available on the internet. I wired up the circuit using the breadboard and was gratified to see that the circuit worked. I got the CPU up display and the keyboard functions worked. To make the fix permanent, I had to cut the tracks to the original socket pins and wire them to the changed signals. This was quite a job as all 28 pins were involved, and I had to reconnect some tracks that went through the pins. The additional 74 LSO4 inverter was mounted on a small circuit board and attached using double-sided tape inside. Once done, I put the EEPROM in the socket, and when powered up, it worked as expected. I also confirmed that the circuit would work with a 2816 EEPROM, which is an electrically erasable ROM chip that can be erased by the programmer and not require a UV eraser. The chip installed now is an EEPROM with a label that I printed. The next issue which I found was that the reset switch was intermittent. It turned out to be the switch itself that was at fault. These switches are almost impossible to obtain new. I was able to cut the switch open and just needed to adjust the spring inside to make proper contact. I then glued it back with super glue. This addressed the problem. Also noticed was a missing nut and bolt on the power supply regulator bar, so I added them. One of the modifications needed to use the ETA3400 expander, which I don't have, is to change the clock speed. I decided to do this mod to speed up the clock from 0.5 MHz to 1 MHz. It involves removing a resistor and capacitor and installing a new resistor, capacitor, and a 4 MHz crystal. I also added the 40-pin connector that's used for expansion, even though I don't own the ETA3400 expansion unit. It would connect using a ribbon cable similar to this one. I was sometimes seeing the unit hang or crash or fail to reset. Pressing on the circuit board caused it to get better or worse. The common problem is oxidation of the IC pins when they're inserted in sockets. Removing each IC indicated that many of them had pins that were black with oxidation. I cleaned them by rubbing them with a soft eraser. After that, the problem went away. Full copies of the manuals were found on the internet. As mentioned, I found the ROM code as well. The manual has a complete listing of the monitor source code. For fun, I entered it on a desktop computer and cross-assembled it using a 6800 assembler. The resultant code matched the ROM image. I also entered the example programs from the manual and cross-assembled them using the CR-ASM assembler, which supports the 6800. I also entered some code for the ET-3400 expander, the monitor, and Tiny Basic, as well as some programs that I wrote. These files are available on my GitHub account at this link. A Heathkit catalog listed the later model, the ET-3400A, as the world's top-selling microprocessor trainer. Tens of thousands are believed to have been made. The ET-3400A was still listed in the 1992 Heathkit catalog, the latest catalog that I have a copy of. It may have still been sold after Heathkit left the kit business, but continued as Heathkit Educational Systems. I'm told that some units are still in use at educational institutions, as well as the accompanying course. This was not the only trainer of its kind on the market, but after using it for a while, I think there were a number of reasons that this was better than some of its competitors, like the KIM 1 and the AIM-65. It was aimed specifically at training. It used high-quality keyboard keys. It offered a breadboard area with access to all signals, power, and clocks. It was self-contained in a rugged case with power supply. There was an extensive, at extra cost, course on digital logic and microcomputer programming available for it. It had a more powerful monitor, including features like breakpoints and dedicated keys than most competitors. It had expansion capability, and it was lower cost, due in part to being offered as a kit. When I started my career as an engineer in the early 1980s, the first programming I did was on the Motorola 6800, so this unit was quite nostalgic for me. I was surprised to find that I even recalled some of the binary codes for the instructions. I'm now thinking about building the ET-3400 expander board from scratch, or maybe design and build an ET-3400A and ET-3400 compatible unit on one printed circuit board. I hope you enjoyed this video. If so, you may want to check out a couple of my related videos, such as the KIM 1 microcomputer and the Heathkit ET-3100A electronic design experimenter.